We'll be starting electrical and electronic measurements. Let's move on to introduction. This is the entire introduction sheet, this as well as this side. Okay, it is a pretty big topic to be covered in one video, so I will be splitting it up in 3 or more parts. Okay, let's get started. Certain definitions when it comes to UPSC ESC prelims perspective. Okay, we can go through it once. We have methods of measurement, direct and indirect. Indirect, what we are doing is we are measuring unknown quantity in terms of standard quantity. Okay, it produces a lot of human errors. Indirect method on the other hand is more accurate and sensitive and preferred over direct method. Then we have types of instrument. We have mechanical instruments which are stable and good for static conditions but are not good for measuring dynamic or transient conditions. Okay, it is heavy and bulky. Let's talk about electrical. These are rapid but have limited time response. Let's talk about electronics. These uses semiconductor devices have small response time, no inertia, high sensitivity, lower weight, lower power consumption. Okay, then we have absolute instruments. Quantity to be measured in terms of physical constants of an instrument. It means tangent, galvanometer and Rayleigh's current balance are some of the examples. Then we have secondary instruments, observing output indicated by the instrument calibrated using absolute instrument. Okay, then we have deflection and null type. And deflection type you are provided with a basis. Okay, PMMC, ammeter, electrodynamometer and moving iron instruments are some of the examples. These are less accurate, less sensitive and have fast response. Then we are going to null type. Okay, null indication decides the magnitude of the measured quantity, more accurate, highly sensitive, less suited for dynamic inputs. Okay, then we have calibration, comparing instrument with primary standards. Then we have certain characteristics expected in a measuring system. These are accuracy, which means conformity to the truth. Okay, precision, reproducibility of measurements, not guaranteed for accuracy. You can reproduce the same measurement again and again, but it is not guaranteed for accuracy. Okay, and precision is proportional to the number of significant figures. Significant figures are magnitude and the precision. Okay, linearity, if the output is proportional to input. Okay, if a system is not linear, which means if the output is independent of input, doesn't mean that it is not accurate. Okay, a system can be non-linear but still be accurate. Okay, let's talk about reproducibility, degree of closeness with which a given value may be repeatedly measured. Okay, then we have static sensitivity. Okay, it's the ratio of output and input measured, its unit is millimeter per microampere or volts as the case may be, defined as small change in output upon small change in input. And we have a new term over here, deflection factor, which is defined as 1 over static sensitivity. Okay, now let's move on to resolution or discrimination. Okay, small measurable input change. If we slowly increase input from some non-zero value, the output doesn't change until a certain increment is reached. This particular increment is called resolution. Then we have dead time and dead zone. Okay, time required by a measuring device to respond to changes to input to be measured is called the dead time. It is also defined as time before which the instrument begins to respond. Then we have dead zone, is the largest change of input for which there is no output. Okay, then we have signal to noise ratio. Noise equals to unwanted signal mixed with the desired signal, leading to some derivation in the output. S upon n. Okay, signal to noise ratio, we expect it to be large in value. Okay, we want its larger magnitude of signal to noise ratio. Then what we are talking about is repeatability, repetition of reading from measuring instrument. Let's talk about error in measurements and analysis. True value, average of infinite measured values when the average deviation is 0. Okay, let's talk about guarantee errors, deviation from nominal value of a particular quantity. It is often given by those manufacturers. Okay, manufacturers have already determined the guarantee errors. Okay, then these are also called limiting errors or guarantee errors. Then we have absolute or relative or limiting error. Okay, error specified nominal value. Then we have error given by this formula, measured minus true value upon true value into 100, or can be actual minus nominal, or you can use this formula as per the given data in the numerical. You can use any of these formula. And then we have this funda over here, 1 upon ER correction is called the correction factor here. Okay, and nominal equals to true and actual value equals to measured. Okay, this is the condition we want but is never achieved. Okay, we have certain errors in the way. Okay, the differences here lies because of errors. Then we have combination of quantities with limiting errors. If you have certain number of data, like this is a data, this is a data, this is your data with certain error, this is your data with certain error, this is your data with certain error, what we want to do is sum or difference. Okay, then we can make the sum, we can add them or subtract them like so. Okay, and this here is the worst possible error. This is your format. Okay, if you are given these data with their respective errors, you can add or subtract them in such a fashion. Okay, this is your worst possible error. Then we have, if you want to multiply, then this should be the format. Okay, if this is the given format, you can multiply. Okay, here the worst possible error is defined by this. Okay, but in case you are met with this particular format, okay, then here multiplication and division are not possible for this one. Okay, then we have power of a factor in such fashion. Okay, this is your required data. Okay, then what we are going to do is we are finding out error which is given by this. If you are having data in this particular format, you cannot use power of a factor method. Okay, for this too, these are formats, and here the power factor is not at all applicable. Then we have special cases over here. We are assuming that resistance are in parallel. Okay, we are having resistance, suppose it is 10 ohm plus minus 10% R2, 20 ohm plus minus 5%. Okay, 10% means it can vary from 9 to 11, and 5% means it can vary from 19 to 21. Okay, so what we are going to do is we are finding out the true value irrespective of the error. We are finding the value. Okay, which comes this. Okay, we are doing resistance of 10 and 20 ohm are in parallel, which is equals to 10 into 20 upon 10 plus 20. Okay, we get this answer. Then we are taking the lower ranges. Okay, the lower ranges, and finding the answer. Okay, parallel resistance combination equivalent resistance. Okay, with lower range. Then we are doing so for the higher range. Okay, 11 and 21 we are finding for the higher range. Then we are finding the percentage error for lower range. Okay, and then we are finding the percentage range for the higher, percentage error for the higher range, like so. Then we are having, well, on solving these two, we get these as the answers. Okay, then we have uncertainty error. Okay, if suppose this is your signal, then uncertainty is given by this. Okay, here you have this particular formula. So this is all for part 1 till here. This is your part 1.